Okay, so in this video, we are considering our third example of optimization. This is problem 6 on the problem sheet of optimization. Let's read the problem. The college plans to build a track 400 meters long around a rectangular field where both ends of the track are semicircles. We want to find the dimension of the field so that the area, so the area of the rectangular field is as large as possible. So here let's draw a picture of the situation. We have a rectangular field, so you can draw a rectangle. And the college plans to build a track that is 400 meters long around the rectangular field, so the track will go like this. But where both ends of the track are semicircles, so we have the track. When we get here, we have a semicircle. And then we continue on the track, and the other end is also a semicircle. So this is our track, right? You have your rectangular field. This could be a football field, a soccer field of some kind. And then you have a track that runs along the rectangular field. At the end, you have a semicircle. Then you keep going around, reach the other end, and another semicircle. So this is your track. We want the track to be 400 meters long. And the question is, find the dimension of the field so that the area of the rectangular field is as large as possible, but where the track is exactly 400 meters long. Well, again, we have here two unknowns. We're asking, well, how long should the field be, and how wide should it be? Well, we don't know, so let's give these two variables a name. Let's call this one y. Let's call this x. Well, what we know is for our semicircle here, if you draw its radius, you can see the radius of the semicircle is going to be half of the width of the rectangular field, right? The diameter of the semicircle is x. The radius is 1/2 of the diameter. So we have a semicircle here of radius x over 2. Okay, so now let's see. What do we know? We know that the perimeter of our picture, being the length of the track, is 400 meters long. Well, what is the perimeter? All right, 400 is our perimeter. Well, look at the two pieces on the rectangular field. There's this part and this part, so it's twice of y, plus this semicircle plus this one. But if you combine the two semicircles as they're equal, they will give you exactly the perimeter of a circle of radius x over 2. The circumference of a circle of radius r is 2 pi r. So what we have here is 2 pi times the radius of x over 2. So we can cancel the 2 over 2, and we're left with, if you write this backwards, 2y plus pi x, and this equals 400. And because again 2y is the length of this side and this side of the rectangular field, the length of the circular path is the circumference of the circle of radius x over 2, and the circumference is 2 pi times the radius, which gives us pi x. What do we want now to optimize? Well, we want to find the dimension of the field, so the values of x and y, so that the area of the rectangular field, and be careful, we are talking here about the rectangular field, so the area of the rectangle only. And we're asking, how do we choose x and y so that the area of the rectangular field is as large as possible? So we are trying to maximize, clearly. the area of our field, but that is x times y. On the surface, it looks like we have a function of two variables, x and y, but if you look at our equality here, we can replace one as a function of the other. Let's isolate y here as a function of x. So 2y will be equal to 400 minus pi x, multiply across by 1/2, and so y is simply 400 over 2, that's 200, minus pi over 2 x. So we can now replace in our expression x times y, x times now this, so 200, minus pi over 2x. And so now we have as our target function, the function we want to maximize, a function of a single variable, x. So here we'll call this f of x. And since we're going to look for critical points, I will actually multiply this x out so as to avoid a unnecessary product rule. So I'll get 200x minus x times pi over 2x is pi over 2 x squared. We're trying to maximize this function. This is a function of x. Again, we have to look at the range of possible x values. Well, let's look at what we have. X is the width of our field, so clearly x is going to be positive. If x is 0, we have no field. How big can x be? Look at this equality. We have 2y plus pi x equals 400. Well, both y and x are positive. Y is the length of the field, x is the width. So once again, and we've done this before, we're adding two positive numbers, and the result is 400. Because they are both positive, they both must be at most 400. So we know that, let me write this here, 2y must be at most 400, and pi x must be at most 400. Imagine simply that pi x, say, was bigger, was larger than 400. Well, if you have a number that is larger than 400, to make it equal to 400, you have to add to it a negative number. But because y is positive, that is not possible. So pi x must be at most 400, and 2y must also be at most 400. But if you isolate for x here by dividing through by pi, you get that x is at most 400 over pi. Of course, if you have an equality here, if pi x is 400, this would imply that y would be equal to 0, which we know is not possible. But if you think of it, it looks like we have an open interval once again. We're saying x is strictly bigger than 0, so we reject 0. X is strictly less than 400 over pi, and we reject the right-hand point. And this is unfortunate because if we only had a closed and bounded interval, we can then use our result about looking at the values of the function at the endpoints and at the critical points inside of our interval. But if you think of it, there is no harm in throwing in 0, because this will clearly not give us a solution. If x is 0, you have no field. The area is 0, which is clearly not going to give us a maximum. So we can dump in our interval 0. And the same thing for this value of x. If x equals this, then pi x is 400. Therefore, y is 0. The field has no length. And the area is once again 0, clearly not giving us a maximum value for the area. So there is no harm in throwing 0 and 400 over pi as the endpoints of our interval. And this will make our life nicer. So x can range over values from 0 up to 400 over pi. And now we're good to go. We're looking to maximize a function that is a polynomial, therefore continuous everywhere, on a closed and bounded interval. So we can only now evaluate the function f at the two endpoints of the interval and at the critical points inside of the interval. Let me just write this like this. This looks a bit weird. So let's find the derivative to find our critical points. F prime of x is quite simple. It is 200 minus pi over 2 times the derivative of x squared, which is simply 2x. Cancel the 2 over 2, and you're left with 200 minus pi x. The derivative is obviously always defined, so you have to look for critical points where the derivative is 0. Send pi x on the other side, and you get that 200 is equal to pi x. Divide across by pi, and so x is 200 over pi is your only critical point. And now we can form our table of values. We have the two endpoints of the interval, the single critical point, which obviously is inside the interval, and we know that the maximum of this function must occur at either the left, the right endpoint, or at the critical point. So we're almost done. Alright, so left endpoint x equals 0. If you just look up, this is your function. If x is 0, this is clearly 0. But we knew this just from the picture. What if x is 400 over pi? Plug it in here, so x over 2 will give you 200 over pi, times pi is 200. 200 minus 200 is 0, and once again the area is 0. Clearly not our maximum. The only other point to check is our unique critical point inside the interval, 200 over pi. And if you look at the function, and again the factored form, this will make the calculation easier. Let's compute it here. F of 200 over pi gives us what? Well, this is 200 over pi. Actually, well, let's just plug it in. Times 200 minus pi over 2 times x. So 200 minus pi over 2 times this value, 200 over pi. Let's see what we get. The pi over pi cancels. 200 over 2 is 100. 200 minus 100 is 100. Times 200 gives you 20,000 over pi. And that is the exact value at x equals 200 over pi. The answer is 20,000 over pi. If you want to get the feeling for this number, although it is obvious in our table of values that this is our maximum value, because the maximum value has to be one of these three values. This is the only positive value, so this is clearly the maximum value that f can attain on our interval. Just to get a feeling for it, let's compute. You'll have approximately 6,366 point roughly And now we're almost done. So we have found the value of x where the area of the rectangular field is as large as possible. But if you remember, the problem was, so let me just write this down. This is clearly the maximum possible area. And since we were measuring in meters, this would be in meters squared. This is clearly your maximum value. And therefore, 200 over pi is the absolute max, or global max. But if you remember, the question was asking to find the dimension of the field so that the area of the rectangular field is as large as possible. Well, we have just found the width of the field, x. What is the length of our field? Right? So x is 200 over pi. And if you compute this, you get approximately 63.66 meters. So this is how wide your field should be so as to maximize its area. And y was 200 minus pi over 2x. So let's see. Y was equal to 200 minus pi over 2 times x, which is 200 over pi. Pi over pi cancels. 200 over 2 is 100. 200 minus 100 is simply 100. So the length of the field is exactly 100 meters. And the width is approximately 63.66 meters. So with these dimensions, a field that is 100 meters long and 63.66 meters wide, the area of the rectangular field is maximized, and the track around the field is 400 meters long. And we're done. Let me make one last little comment. What if you didn't think about this observation, that 2y plus pi x were adding up to 400, and because both y and x were positive, 2y and pi x were positive, and when you add positive numbers that add up to a fixed value, they both must be at most the given value. And this is with this observation that we got the right-hand point of our interval. Suppose that you miss that you don't see from this equality that pi must be at most 400 over, that pi x must be at most 400, therefore that x must be at most 400 over pi. Can you still solve the problem? Well, let's see. If you miss this, and you don't have your right-hand point, and all you would say for your interval would be x is positive. Then you would have an open interval, and so you would have to produce a rough sketch of the graph of the function, which is not as nice, but here, not that hard either. Look at your derivative. You found a unique critical point, and of course, at this point, the derivative was 0, and you would ask, is this point a minimum or a maximum? Well, you're looking for concavity. Look at your second derivative. This is the first derivative. Differentiate one more time, you get the second derivative. The derivative of 200 is 0, minus pi times the derivative of x, which is 1, and all you get for your second derivative is negative pi, which is a constant, and more importantly, a negative constant. So the curve would be always concave down. So think of how simple your graph would look like. You have a unique critical point of 200 over pi, and when you plug this into your function, as we did here, you'll find this value of 20,000 over pi. You know, at this point the curve is flat because the derivative is equal to 0 when x is 200 over pi. And because the curve is always concave down, you know that the graph will look like this forever. And so indeed the value x equals 200 over pi is your absolute maximum. Or if you prefer, your global maximum, same thing. And you see that you have a rough sketch of the graph of the function, and you still have found that this value of x gives you the maximum possible value of the function, and then again you can solve for the y value, going back to this equality, replacing x by 200 over pi. So personally, I prefer to have a closed and bounded interval, but the observation that both 2y and pi x had to be less than 400 because they were both adding up to 400 and non-negative, giving you that x was at most 400 over pi, was not entirely obvious. So if you ever cannot find a way, even though there is one, to obtain a closed and bounded interval, fall back on the second derivative, helping you producing a rough sketch of the function, showing that you have indeed either a minimum or a maximum. And as we have concluded, the field will have maximum area if the length is 100 meters and the width is approximately 63.66 meters. These two dimensions will maximize the area of the field and give us a track that is 400 meters long. And that's it.